Hello, everybody. Welcome to today's KAN seminar. Today we have two speakers, two talks. Our first speaker is Dr. Manil Mohan. The title of his talk is Error Estimates for viscous Berger's Equation Using Deep Learning Method. Dr. Manil Mohan is an associate professor in mathematics at IIT Roorkee. He earned his PhD from Indian Institute of Science Education and Research TVM and has held postdoctoral and faculty positions at institutions in India and also US, including the Air Force Institute of Technology, US. His research focuses on deterministic and stochastic PDEs, fluid dynamics, control theory, and inverse problems. He has published over 100 papers, supervised 5 PhD students, and currently mentors 5 research scholars. He is a recipient of several awards, including the Inspire Faculty Award and IIT Roorkee Outstanding Teacher Awards 2024. And he is a member of the Indian National Young Academy of Sciences. With that short introduction, the floor is yours and you can start your presentation.
Thank you so much, Professor Kanyadakis, for this invitation. And so today I'll be talking on the error estimates for viscous Berger's equation using deep learning method. To be frank, like I am not from this area. We have just started working in this area, and we were able to produce some results. And this is a joint work with my postdoctoral student Wasim Akram and my PhD student Sagar Gautam, and one of our collaborators, Dibamshu Verma. And in this talk, we will be deriving some error estimates for viscous Berger's equation using deep learning method. So as all of you know, deep learning has emerged as a powerful tool, not only in the traditional AI domains, but also scientific computing, particularly solving complex partial differential equations. And nowadays, like in the recent years, several really good works are coming, and physics-informed neural networks offer mesh-free approach by embedding the governing PDE and its boundary or initial conditions into neural network training process. And pins are as I mentioned, it is a mesh-free approach. And of course, if you look at the classical or traditional methods in numerical analysis, like finite element methods and all, they always depend on mesh. So it is a mesh-free method. Pins minimizes point-wise residuals of the PDE, allowing for flexible and efficient approximation of solutions, making them a promising method for analyzing problems like Berger's equation, 2D Navier-Stokes equation, and much more physical problems should be explored more also. And we are talking today on the Berger's equation, and it is a fundamental nonlinear PDE with applications in fluid mechanics, and it can consider as a toy model for the famous Navier-Stokes equations, and serves as a benchmark problem for several problems. And of course, it is a benchmark problem to assess the performance of pins. And understanding the error behavior for pins based on solutions is crucial for evaluating their reliability, grading improvements in neural network architecture, and training strategies. So with this introduction, let me go to the problem. Consider a PDE. Say, suppose you consider LU equal to F in omega. You assume that omega is a convex domain, or with the domain with the C2 boundary, and you have a boundary data U is equal to G on gamma. Suppose L is a differential operator, and this problem can be treated as a minimization problem. Suppose you find the infimum of U in an appropriate space of, you find the norm Lu minus F the whole square plus U on the boundary gamma minus G the whole square. And as you know, like if you minimize this problem, so when you take the minimum, the absolute minimum occurs at 0, and that is happened to be a solution to the previous problem. So if a problem is well posed for this minimization problem as a unique minimizer, and the minimum value is 0, and you will get the U as the solution of the first PDE that I have taken. Now, in the neural network framework, what is happening? So the optimization is typically performed in a discrete setting. So we are taking, let Fn be a finite dimensional function space defined over a bounded domain omega. Select a set of interior collocation points, say xj, starting from j equal to 1 to m, subset of omega, and the boundary points yj varies from j equal to 1 to n, subset of the boundary. then the objective is to find the infimum of u in n such that this quantity is minimized. Lu of xj, xj's are from omega and yj's are from boundary. So for any u, the error is this error norm of Lu minus f the whole square plus u on the boundary minus g is called the residual error. We call it as a residual error. Now this is the algorithm, and most of you might have seen this algorithm several times. So here x1, x2 are the variables and t the time variable. So these are hidden layers, and you are computing here. It is an illustration of pin algorithm for solving a PDE, especially in the case of we are taking Burgers equation with a loss function, specifically formulated as the Burgers equation here. You can see u theta t minus new Laplacian u plus summation I equal to 1 to n u xi minus f. This is the residual error, and u here we are assuming boundary data to be 0. That's why I'm not considering any minus g here with the initial condition. And of course, if the loss is less than epsilon or the maximum error is iteration is occurred, then we can stop the process. Otherwise, we continue the process. And let us come to our model. So let omega subset of Rd, we are considering here domain D equal to either 2 or 3, be a convex domain or a domain with a C2 boundary, say gamma. And we are considering du by dt minus new Laplacian u plus summation u du by dxi equal to f of xt in omega cross 0t. I'm here taking boundary data to be 0, but we can take boundary data to be any boundary data also, not a problem. For a simplicity, I have taken 0 boundary data because you will see in a moment that naturally boundary data will come when you go for deep neural networks. And here, this is a second order term minus new Laplacian is a linear term. This is a non-linear term. Sometimes people will call it as a convective term. So there is an interplay between this minus Laplacian and this convective term. And for if for un in fn, the residual error is less than epsilon greater than 0, our aim is to show that the un minus un, u is the original solution and minus un is from the fn, the deep neural network fn, it is less than or equal to c epsilon. So if the residual error is less than epsilon, our aim is to show that we have already defined the residual error here. If the residual error is less than epsilon, our aim is to show that the actual solution minus the DNN solution will be less than or equal to c times epsilon. Conversely, we seek to demonstrate the existence of a DNN, UN in Fn such that the residual error is less than any given epsilon positive. So we have two aims. One is for a UN in Fn. Suppose the residual error is less than epsilon. Our aim is to show that the original solution and the DNN solution is less than equal to c epsilon. Conversely, if we want to demonstrate the existence of a DNN, UN in Fn such that the residual error is less than epsilon for any given epsilon positive. Moreover, we will study some stability analysis also, the difference between two DNN solutions. And the same problem, you can ask for stationary case also, for stationary Burgers equation also. So the question is not only here for only for time-dependent problem, we can analyze the problem, same problem for stationary problem also. But our main focus is on the non-stationary problem, and at the end I will give you some glimpse on the stationary problem also. So like UN in Fn may, I told you in the beginning also, UN in Fn may have a non-zero boundary data. So the main thing is, or challenging thing is, we need to consider a Burgers equation with the non-homogeneous boundary data also. That is also our important, one of the important aims. So the first question is, when you have a system, we have to talk about the well-posedness of the system, whether this system is well-posed or not. Here the well-posedness, I mean the existence and uniqueness of a global strong solution. That is the meaning of a well-posedness. And let me tell you, the well-posedness is already known due to Leditsky, like even 50, 60 years back. But there, the thing is that she has used some principle to prove the well. Need a particular forcing term which is in L2 0 to L2. So we need a global solidity result for that particular forcing term. So we are considering the well-posedness of the Burgers equation with the non-homogeneous boundary data for that particular forcing. So this is our Burgers equation, as I have already mentioned. Now, what is a strong solution? So strong solution given here means, suppose your F is in this space, L2 0 T L2 omega. Okay, and the initial data is in H01. So the initial data you take in H01, that is the Sobolev space, whose first order weak derivatives are L2. If these two conditions are satisfied, suppose these two conditions are satisfied, then the question is, can you find a function which is continuous in time as a function in H01 omega and L2 0 H2 omega with its derivative or with the weak derivative with respect to t belongs to L2 0 L2 omega, or this equation 1 is satisfied for almost everywhere in L2 omega. This is the question. Can we find for a given u naught in S01 and a given f in L2 0 L2, can we find a solution which is in this equation is satisfied almost everywhere in L2? Now, this is the main theorem. This is the existence theorem for this problem. Of course, the answer is yes. This is true in 2 and 3 dimension also. Suppose u naught in H0 omega and f is in L2 0 L2 omega. There exists a unique strong solution u in L infinity 0 H0 omega with L2 0 domain of A. Now, I will give in the next slide what is the domain of A. Domain of A here means L2 H01 omega with A defined as minus Laplacian. So here A I am defining it as minus Laplacian with the domain of A as H2 intersection H01 omega. Moreover, this energy estimate is satisfied. So there exists a unique strong solution for this problem. Now you may ask a question like, this were Burger's equation and I told you that there is a relation between Burger's equation and Navier-Stokes equation, because Burger's equation is a toy model for Navier-Stokes equation. Remember, Navier-Stokes equation is a vector valued equation and Burger's equation is scalar valued equation. So here we are able to prove the well-posedness in 3D also. But for the Navier-Stokes equation, the well-posedness in 3D or the global strong solution in 3D is a well-known open problem. So the method what we are explaining here may not work for the 3D Navier-Stokes equation regime. So now, what is the idea of the proof? The proof is in, like I can say, 2 steps. The first steps, we are proving the local existence. So what we are doing here, for P bigger than D, we are taking a U naught, which is in LP, and F, which is in L infinity 0 to L2. Then we can always find a unique local mild solution for our previous problem. With we cannot find like for all time, up to a certain time, like up to time t star, such that our solution belongs to C0 to LP for sufficiently small t star. Okay, and the solution is satisfied in this mild form. Now, what is the idea? The idea is quite simple. You define it as a mapping. The right hand side as a mapping, say gamma. So gamma u, you prove that by Banach fixed point theorem, gamma u as a fixed point. That means gamma u equal to u. Up to a certain time, you will get the unique fixed point for your problem. Now here, what is B of u? It is nothing but just notation, summation I equal to 1 to d, u du by dxi. And as I mentioned earlier, A is the Dirichlet Laplacian, which is minus delta, and the domain of A is H2 intersection H0 1. Now, the question is, you have a local existence for the problem. How will you go from a local existence to a global existence? This is the next question. Now, suppose you are given a u naught in L2, H0 1 O, and F is in L2 0 to L2. You know that CC infinity is dense in H0 1 omega. So since given any u naught in H0 1 omega, we can find a sequence of functions in C0 infinity omega such that n will converge to u naught as n go into infinity. That's what I am explaining here. There is a sequence u naught n in CC infinity omega such that u naught n will converge strongly to u naught in H0 1 omega, and a sequence Fn in CC infinity of 0 t cross omega such that Fn converges to Fn L2 0 t L2 omega. Now, what our previous result says? Our previous result says that there exists a unique, because our function satisfy the previous result, all C0 infinity functions P. So, and if CC infinity 0 t cross omega, all in L infinity 0 t L2, there is a unique mild solution up to a certain time t star. And for any d between P between d and 2d minus 2, it is because of the Sobolev embedding. We obtain the existence of a local mild solution for this problem such that un converges to un C0 t LP. Okay. Now what we can show, because it is a smooth solution, you know that if you have a smooth solution, we can apply the absolute continuity lemma. By using the absolute continuity lemma, you can take an inner product with the UN, prove appropriate energy estimates, and then show that the sequence converges to a solution, to a strong solution to our problem. That's what our existence of a global strong solution for our previous problem. Now, as I mentioned earlier, our DNN, when you work on a DNN, the solution may not be zero on the boundary, because you will be having non-zero quantities on the boundary. But there is always an error. So equation satisfied by DNN may have a non-zero boundary data. So we have to deal with the non-zero boundary data. So in the PDE literature and all, if you look into it, there are two ways to deal a problem, like a non-stationary problem, either through a elliptic lifting or through a parabolic lifting. So there are two ways. So what I am going to present here is a parabolic lifting. So what is a parabolic lifting? What we are going to look at, we are going to look at a non-homogeneous heat equation first. So given dc by dt minus new Laplacian z equal to 0, with z equal to g on the boundary, and the initial data I am taking to be 0. So this is a non-homogeneous heat equation. And what result is known due to Lyons and Manganese. It's a very famous book, and from that book we can see that for any g belongs to h half 1 by 4 gamma cross 0t, you may feel like that space is a little bit different looking space, but that space is nothing but L2 0t h half of gamma intersection h1 by 4 0t L2 of gamma. If you consider a G in this particular space, then you can find a solution, a unique weak solution to the previous problem. Here, what is unique weak solution? Zn L infinity 0 t L2 intersection L2 0 t H1, such that this derivative belongs to L2 0 t H minus 1 omega, and this energy estimate is satisfied. So this energy estimate is satisfied. The right hand side we can see it is estimated entirely in terms of H1 by 2, 1 by 4. Now, moreover, if G is in a better class, what is that better class? G belongs to H 3 by 2, 3 by 4. You look at like a little bit carefully. Whatever the index comes here, its half is coming here. H half 1 by 4. H 3 by 2, 3 by 4. So if you take H S by 2, you will get S by 4. That is the idea. Okay. So if G belongs to H 3 by 2, 3 by 4, gamma cross 0t, that means L2 0t, H3 by 2 intersection H3 by 4 0t L2 gamma. Then a unique strong solution exists. That means if Z belongs to L infinity 0t H1 intersection L2 0t H2, such that the derivative belongs to L2 0t L2. And this energy estimate is satisfied. So these are two important results for us, especially for the non-homogeneous heat equation. Then, as I told you, what is a lifting, parabolic lifting. So what we are going to do here, you have a non-homogeneous Burgers equation, which is given by system 4. The important thing is y equal to g on the boundary. Okay, that's what our non-homogeneous Burgers equation. Now, what is the lifting? Basically, we want to take an equation where our boundary data to be 0. That's what our aim is. You look at here, I have chosen my solution of my non-homogeneous heat equation, the same boundary data I have chosen, z equal to g. So if I define a new variable, w equal to y minus c, then what is going to happen? Y is also having the same boundary data, z is also having the same boundary data. So my y minus z will have a 0 boundary data. So that is the idea, parabolic lifting. The same thing you can do with a elliptic lifting also. Let me tell you, you can consider, instead of a parabolic problem, you can consider elliptic problem also. Okay, that will give you not this regularity result, some different regularity result you will get if you use a elliptic lift. So change the variable by using the change of variable, w equal to y minus c, then w satisfies this equation. So look at this equation, you carefully look at this equation, you will identify one thing. The first three part looks like our perfectly it aligned with our Burgers equation. Next two terms, you may think like they are different terms, but no. They are actually perfectly very good terms, because these are two linear terms. So that is, dealing with them is very easy, not a difficult task. And you have already estimates on Z in H1 omega, Z in H2 omega. So these terms are this term as well as this term can be handled very easily. Not only that, they are like Z is known to us, the regularity, because Z bound already known to us. Here we can always estimate in terms of G. So this term can be estimated in terms of G. Other two terms are linear. The only thing is we have a right hand side now, which is depending on F and this Z. That was the solution of our previous problem. Now the question is whether a solution exists for this problem 5 or not. Of course, a unique global strong solution exists. How we can prove? We can prove in the same way as in the case of Burger's equation with the zero boundary data. There is not much difference from the Burger's equation because only two extra terms are coming, which are these two terms. That can be estimated using our previous Z through Z as well as our yes. So any question? Okay.
Yes. I have one short question.
Yeah, please.
The source term on the right-hand side, the derivative dz dxi.
Yes.
Wasn't z is an L infinity function, so this derivative is a distribution, or can
that is not L infinity because I'm not taking as you can see here.
Yes.
This is exact. Z is appearing here because it's H1 estimate. So it is H1 estimate L infinity
function.
Yes, it is a function. Yes. Okay. So I will estimate that actually. In fact, I will estimate this particular term. Okay. In the next slide. So that's a good question. How we will prove that this is in L2 0 to L2. So that's what I have done here. In fact, it is a function. It is not a distribution, it's a function because you can estimate that quantity in L2 0 to L2. So already we have a regularity of Z. We can take the L infinity supremum norm of gradient Z outside. So L infinity norm will come here. So you apply augments inequality in 2 and 3 dimension. You can apply augments inequality. So in 2 dimension, you will get L2 norm and S2 norm here in with the power half and half. But for 3D space, you will get 1/4 and 3/4. So you will get S2 here and L2 here. So in 2 and 3 dimension, you can estimate the L infinity norm. And already we have proven, we have estimates for Z here. So with that, we can show that, as he told, it is not a distribution. Actually, it is a function. It is in L2 0 to L2. So as Y0 in S01, we obtain a unique strong solution. W in L infinity 0 to S01 intersection L2 0 to S2 of the previous equation. We get a unique solution for this problem. And therefore, our equation, this equation admits a unique strong solution for our problem with Y in L infinity 0 to H1 with L2 0 to H2. So this is the global solvability result for non-homogeneous Burger's equation. Okay. So this is the existence of solution for any given T positive Y0 in H01 omega with G in H3/2, 3/4. The equation, the non-homogeneous equation admits a unique strong solution with Y in L infinity 0 to H1 intersection L2 0 to H2 with the derivative belongs to L2 0 to L2. So now let us come back to the system satisfied by DNN. So we remember the Burger's equation already I have written here. Then the approximated DNN solution, as I told you, may not satisfy the above equation exactly. Indeed, we can assume that there is some error. Such an error in the equation may be an error that I am denoting by F tilde. Error may be on the boundary and error may be on the initial data. So system satisfied by DNN will be something look like this. dun by dt, this left hand side is exactly Burger's equation. This is the error, like the error of in F tilde and F. This is the error in G. If you take a non-homogeneous boundary data, you just need to take G minus G tilde. That is the only difference. That's why I told you for simplicity, I took 0 boundary data. And UN of X0 is U0, this is the error in the initial data. Okay. Now we aim to show that if these errors are small, then the corresponding DNN, the corresponding solution, the deep neural network solution UN and the exact solution are also close enough. they are also like differ by an epsilon. So this is a result. So what does this say? Suppose U naught is in S naught 1 and F is in L2 0 to L2, and let U be a unique strong solution of our Burgos equation. Then for any given epsilon positive, there exists a UN in Fn such that this is my F tilde and this is F. So the distance between F tilde and F, similarly UN on the boundary, which was nothing but G tilde, that is the difference of the 0 and G tilde, and U naught and UN. Suppose there is a UN satisfying this condition, less than or equal to epsilon square, then we can find a C positive such that the actual solution U and UN in the L infinity 0 to L2 norm intersection L2 0 to H1 norm, this is less than or equal to same order, whatever epsilon we are getting here, same order we are getting here. So this is what we want to prove. So that means that what is our aim? Suppose U is a unique strong solution to the Burgos equation, and suppose you assume that there is a UN in Fn such that the error, that means F tilde minus F, this is my F tilde minus F, okay. So this is in L2 0 to L2 with the UN on gamma. So UN, this is minus G tilde, which is less than, and this is a norm I'm taking H of 1 by 4 with the U naught UN. Remember, I'm not taking the higher norm here, I'm taking only H of H1 by 4 only. With the U naught minus UN 0 less than or equal to epsilon square, then we can find an C positive such that our solution will also be close enough. That's what our aim is. So the idea is, idea of the proof is this. So I can call let F tilde equal to this quantity, the bracketed quantity, which is I am calling it as F tilde, and minus G tilde equal to UN, so that this UN will satisfy this equation. You define W equal to U minus UN, and you can easily see the linearity, bilinearity of the operator, bilinear operator, because it is linear in both the variables. You can write the fold function in this way as 3 different terms, so that the system satisfied by W will look like this. This is a system satisfied by W, where W is the difference U minus U1. Now, again, what we can do, here you can see that the problem is, of course, the problem is non-homogeneous. W is on the boundary G tilde. So, since UN are smooth, we are taking smooth solutions of the smooth solution of the DNN solution, and bounded data we are assuming 3 by 2, 3 by 4. So we know that if you consider a bounded data G tilde belongs to S 3 by 2, 3 by 4, then the corresponding heat equation, I want to use the elliptic lifting here. So corresponding heat equation will have a solution, will have a strong solution for our corresponding non-homogeneous problem. And then by defining a new variable V, which is W minus Z, that you will get V equal to 0 on the boundary. You may see several extra terms there. It is not that much terrifying terms. Most of them are linear, and several terms will be in terms of Z and dC by dxi. That can be estimated by using Z, which has a better regularity. Already we have better regularity for our solution. So that is a plus point, or that is a good point for us. Now what we can do, take the inner product with the V to the first equation, use the absolute continuity lemma, because you can use absolute continuity lemma. The reason is that we have a smooth solution for this problem. And then taking integration by parts, you integrate by parts also, you will end up, several terms will go away or cancel each other, and you will be ending up with these 4 equations or these 5 terms. And by using several applications of Holders, Ledzinska, Poinger, Young's, at the end of the day, you will be reaching at this problem or this estimate. So I didn't give you several steps. In between, we had to estimate all the 4 terms, all the 5 terms in different ways. One can use the classical Holders, Ledzinska inequality, as well as Poinger, because we are working on bounded domains, we can use Poinger inequality. At the end of the day, we will be reaching at this level. This is our final estimate we are getting. And you can see here, norm of V is coming here. You have a norm of V here also. Just to apply an application of Grunwald inequality will give you, an application of Grunwald inequality will give you that this term the norm of v square plus nu time gradient v square is less than or equal to this term. So you can see that the right hand side is now independent of, there is no v is appearing there, and whatever the term is appearing, for example, gradient z or gradient, this is also gradient z, gradient u is the original solution. All these terms can be estimable. So there is no problem in estimating all these terms. So that means that the whole exponential term considering containing here are finite. And remember, what is our VO0? VO0 is nothing but U0 minus UN, because V definition is W minus Z. Z is 0 here, and W is U minus UN. So VO0 is U0 minus UN, which is less than or equal to epsilon square. That's what our assumption was. This is less than or equal to epsilon square. Second term, F tilde. So here you can see here F tilde in H minus 1 omega. And you can see here our assumption says that this is my F tilde. So that F tilde is also bounded by, because that is my F tilde. F tilde is also bounded by, first it is H minus 1, and H minus 1 norm can be bounded by L2 norm by using Poincare inequality again, and you will get less than or equal to C epsilon square. And these estimates, L4 norm of Z2, you can take the supremum of this quantity outside, because again you can use Sobolev embedding to show that these norms are finite, which is also less than or equal to epsilon square, because the difference is we have taken already Z, what we have taken, Z is solution of this one estimated in terms of G tilde, because Z satisfies this equation. You can see here Z satisfies this equation, this as well as this, and if this is less than G, in place of G it will be G tilde, and we have already assumed that the UN on the boundary H1 by 2, 1 by 4 is less than or equal to epsilon square. So that is also less than or equal to C epsilon square. Of course, gradient C is also less than or equal to C epsilon square. So the whole term is less than or equal to C epsilon square, and we are done with the error estimate. So it is less than or equal to C epsilon square, and recall that U minus UN is nothing but W, which is V plus Z, and from there we are getting U minus UN is also less than or equal to C epsilon square. This is a proof for the first part. What we have proven here is, suppose we have a there exists a UN in Fn such that these differences are less than or equal to epsilon square, then the solution and the DNN will also be close enough. That's what our first result was. Let us come to our second result, the question of existence of DNN. That is the next question. So the existence of DNN for a given epsilon positive, we can find there exists a UN in Fn.
Neil, can I ask a question?
Yes, yes, please.
So you have N here.
Yes.
N refers to the number of neurons, for example, the size of the
Yes.
network. So that, but I didn't see you. I mean, how does the network come in? Because it's a discrete version, but other than that, you haven't really used any properties of the network or the network space and so on.
Exactly. We didn't go to that detail, because our aim was to only prove the error estimate. So we didn't go to the particular neurons and then checked. We only checked with the numerical computation.
But what assumption are you using for the neural network space?
So
that should be applied directly to the UN.
Yes.
Maybe your space FN.
Yeah. Like you are talking about, we are having this result also. That I was coming to this.
Okay.
So,
okay. Maybe yeah. I can wait.
Yeah. So we are coming to that actually. Yes.
Okay.
Yeah. So yeah. So for any given epsilon positive, there exists a UN in Fn such that the question was whether such a UN in Fn exists or not. So yes, that exists. Like we can show that there exists a UN in Fn such that this condition is satisfied for some C positive. So this is a result from C and cow. So it is like a let us, as he told also, like how will you represent such a neural network, like a deep neural network. So the result of what available was, suppose sigma is in C infinity of R, with the sigma n, the nth derivative here, not equal to 0 for all n, and k is any compact set, then any f in Ck can be, for any f in Ck of k, we can find a function phi n represented by a deep neural network with complexity n. Such a phi n exists, and that phi n, like any alpha, this is a derivative of f, any alpha the derivative of f can be approximated by this phi n in the Ck norm in this order. This order 1 by n k minus mod alpha by d, supremum in this norm, and holds for all multi-index alpha with mod alpha less than or equal to k and mod beta equal to k. And this is available result, and what we have done here, we have reduced this result from Ck to HM now. That means by using a density argument, for any f in HM intersection H01, we were able to, for any given epsilon positive, we were able to find a function phi n represented by a deep neural network with the complexity n. We prove that such a deep neural network exists such that f minus phi n in HM less than or equal to epsilon. So that's what we have proved. And Professor Karnataka, I don't know, like we have done this much part only. Like we didn't go into more details of this n and like a number of neurons and all.
I think this is a result that goes back to Horning, right? Long time ago.
Yes. Yeah. But maybe like I have like we have seen in this paper, but we might have we have to go back and see also. Yeah. So this was like we are generalized into this HM space, the Sobolev spaces, and we didn't go to the number of neurons and all. Yeah, that I can say.
Okay, thank you.
So now, as I mentioned, suppose U is a strong solution of Burgers equation. We find a UN in Fn such that U minus UN, we already found less than or equal to epsilon, and by using a absolute continuity lemma, and the second estimate in this one will give us that the U minus UN in C0 to H1 is less than or equal to this, and by our previous result we can approximate by phi n's, and we will get less than or equal to C epsilon. And using the Burgers equation, of course, recall from the triangle inequality, you just add and subtract. F is nothing but the Burgers equation, and then use the previous result. You can always see that this is our assumption, like this is less than or equal to epsilon from like 12 and 13. Here we have this assumption. These two conditions we have. From there we are getting the initial data is bounded, derivative is also bounded, the Laplacian term as well as the convective terms are also bounded by epsilon, as well as these terms are also bounded by epsilon square. And further note that L infinity 0 to H1 norm can be, you add and subtract U minus UN in, this is a bounded quantity, and this is less than or equal to epsilon. And on the boundary also, U minus UN is on H half you take, it is bounded by this is a trace. You can apply the trace inequality here actually to come from H half to H1 by using the trace estimate. You come from H half to H1, and that can also be bounded by epsilon times some constant depending on the trace actually. And from here, comparing the estimates like previously what we got earlier with 15 and 16, these two estimates, we obtain our required result 11, which is this estimate, the existence of a UN satisfying these conditions. So now finally the stability result. Suppose we have there are different NKs. So, we are considering a UNK from FNK for k equal to different deep neural network solutions. We are considering approximate solutions DUT by DK. We satisfy two different the Burgers equation denoting by k with this condition such that their difference, like their solutions are bounded by epsilon square. That means their difference, you consider minus Fk plus UK on the boundary as well as the initial data, they are bounded by epsilon square for any epsilon positive. Then you can show that the difference between UN and UN1 and UN2 in the L infinity 0 T L2 norm as well as L2 0 T H1 norm is bounded by epsilon square and the initial data as well as the forcing. So the stability of the deep neural network also you can establish for the Burgers equation. And so as I told you, I'm not a expert in this area. This was done by my collaborator Deepanshu, and I'm not like I'm a purely theoretical person. So he computed this result, some numerical simulations he has done, and this is for the true solution U, which is he has taken this domain omega equal to 0, 1 cross 0, 1 with the time t in 0, 1, and the pin architecture is fully connected neural network of depth 2 and width 32. By using this is the exact solution that we have obtained, and this is a predicted solution by DNN, and these are some numerical results. And here are some error estimate. Let us recall that the loss function, it was of the order of epsilon, and we were able to find a C which is order of epsilon, and you can see H1 error here as well as residual error. So this is H1 error versus the residual error. These are some numerical results. And of course, I mentioned in the beginning that we can find the stationary Burgers equation also. So the difference is here, time dependency is not there, time independent problem. So this is the time independent problem, which is omega subset of RD with D into 3. It's a converse domain or domain with a C2 boundary. And then this is a time independent problem, where nu is positive, F infinity is given forcing term. Let me tell you one important thing here. Here the strong solution exists without any problem. But the uniqueness is only true for there is a relation between nu and F infinity. But we only work for like a particular strong solution. So for F in L2, we always get a strong solution for our problem. So let U infinity be a strong solution to the problem. Then there exists a DNN U infinity such that suppose our U infinity minus UN is less than or equal to epsilon, then our error which will be less than or equal to epsilon square. So here the constant will also depend on the trace inequality. So here also the question is like you will always get a non-homogeneous problem, and then here the idea will be like you can transform into either you go to a elliptic lifting and transform into a zero boundary condition and then work. So here the error estimate will be like this. Let F infinity belongs to L2 omega and U infinity be a solution to the stationary Burgers equation. For epsilon positive, there exists a solution U infinity in Fn with the U infinity H2 less than or equal to M, and the difference is less than or equal to epsilon square. Under the condition nu, as I told you, there will be always restriction on nu and the depending on nu and forcing of order, and there is a constant C such that order is like we are not getting exactly epsilon, we are getting order of epsilon to the power 2 by 3 only. But under further assumptions, here we are taken L2, but if you take HF on the boundary, suppose you take only L2 on the boundary, you will get epsilon to the power 2 by 3. But if you take HF on the boundary, then we will get exactly epsilon. And these are some numerical solutions for the stationary problem. And these are some references. Of course, the first paper was our motivation, where they have considered the error estimate for deep learning methods for fluid dynamic problems. But we found some inconsistencies there in the paper, and we are currently working on the same problem, for the fluid flow models with in 3-dimensional Navier-Stokes equation, at least in the stationary case, and 2-dimensional Navier-Stokes equation for the non-stationary case. We are trying to relax their conditions and all to get some error estimate for DNN, and these are some another very good. Of course, the PAN paper by Kannada et al. Is a fantastic paper, and thank you all for your kind attention. Thank you so much.
Thank you so much for your great talk. Now we open the floor for questions. Do we have any questions for the speaker? I saw somebody raised hand during the presentation, but I don't know. Yes.
Yeah, sorry.
Can you first introduce yourself?
Yeah, I'm Matthias Erd from University of Wuppertal in Germany. So I raised my hand at page 21. So this was these approximation theorems, and so the theorems are formulated in a way that they are not constructive. So for an applicant, like here from the Brown group, they would ask you, I mean, what kind of network, what kind of activation function I should select.
We use the TANH activation function. That's what I remember correctly.
So I mean, the theorem itself is not constructive, but maybe the proof. Maybe in the proof there's a hint how to select the activation functions.
Yes.
Yeah.
Yes, you are right. Like we have used the C infinity activation function, like a TANH activation function. That's what I remember. Of course, like this is what I remember, like a C infinity function. For example, also we have taken TANH as the activation function. As far as I remember, that's what I remember.
Yeah, thanks. Maybe just another idea I had was for the future directions one could think about include cross diffusion. So mixed derivatives. This is also quite important in applications.
Yes.
And it would be another challenge for the analysis.
Yes. You sure. So we will try to do that. Yeah. Thank you.
Thanks.
The bigger challenge also is the implicit case.
Yes. No doubt. Yes.
Because as you go to Reynolds number, I mean, to the flows, you want the Reynolds number to go high. So, but I don't know if anybody has actually. I don't know if anybody in the audience knows if anybody has shown that the implicit Berger's equation can be approximated accurately by pins.
In the implicit case, you have shocks, and then the whole functions they must change.
I mean, the weak solution. Let's say the weak formulation, like HP. What we do with the variational pins.
Exactly. That's a good question. Yes.
We have for variational pins, we have results for elliptic and parabolic, but not for Berger's.
Oh, okay.
So variational pins is basically you hit it with a Legendre function integrated by parts. So it's like a Petrov-Galerkin method.
Okay.
So the test functions are smooth, but the trial space is the neural network.
Okay. Yeah, that is a good idea. Yes.
Yeah.
Yes.
So it's a weak solution, not strong solution. So
yes, of course, one has to work with weak solutions, not with the strong.
Do we have any other questions, comments?
Hi, Dr. Mohan. This is Kyle from Brown. Yeah, thank you for this amazing talk. And I just have one, maybe a little bit stupid question. So, where in the in your work, do you rely on the specific structure of the nonlinear term in the Berger's equation? Like, does all of these arguments can I carry all of these arguments over to cases when I have different forms of the nonlinear term, like diffusion reaction equation with a different nonlinear reaction term? How does the arguments carry over?
So like, of course, the nonlinear term is here. It is a bilinear term. That means it is linear in both the variables. It is not a nonlinearity which is it is a polynomial of order 2 only. That is one important thing. It is a linear in both the variables. And another thing is so there is advantage if you apply, for example, here the heat semigroup estimates and all. So it will give you some kind of there are some heat semigroup estimates nonlinear estimates we are using there. So that if you use a general nonlinearity, there may be issue coming here, but you may get a local solution, no doubt. But while you come to prove the non-local solution or the global solution for this problem, here, suppose you have a extra nonlinearity here, so it will depend on what the growth of the nonlinearity. that will surely depend. It cannot grow arbitrarily large or something. It is a maybe polynomial order. I think it may be possible, but still I am not sure. But at least you have to think about the Sobolev embedding, because we are looking at the L20T L2 or L20T H1 or L20T H2 solution. So we cannot arbitrarily take any non-linearity. And of suppose simple heat equation with the right hand side having some polynomial power. So you will always get a blow up of solution also. Even the classical solution blows up in finite time. Yeah.
Yeah, I see. Thank you.
And one more important thing, here there is a speciality. When you take inner product with U to this equation, that term will vanish. That is another property of Burgers equation. So that term won't play that much when you take inner product with U. That is also a good thing. Yeah.
Do we have any other questions for a speaker from the audience? Okay, since we don't have any more questions and our second speaker is here, I would like to thank you for staying up late for this presentation. We enjoyed and it was very, very useful. Thank you so much.
Thank you so much. Thank you, Professor Kanadakis, for the invitation. Thank you. Bye.
Bye. So it's time to move on to our second session. Thank you so much. Our second speaker is Dr. Changhong Mu. He will be giving a talk on Energy-Dissipative Evolutionary Kolmogorov-Arnold networks for complex PDE systems. Dr. Mu is a postdoctoral researcher in the Department of Mathematics at Purdue University, working with Professor Guan Ling. From 2012 to 2024, he served as a Van Vleck visiting postdoctoral scholar in the Department of Mathematics at the University of Wisconsin-Madison. He earned his PhD in mathematics from Virginia Tech. His research primarily focuses on data-driven reduced order modeling, data assimilation, and machine learning with application in turbulence and geophysical fluid dynamics. With that short introduction, the floor is yours and you can start your presentation.
So first of all, thank you for the introduction and thank you for the invitation. It is really my great pleasure to give this talk in this seminar. And I'm really grateful to have this opportunity to present what we have done in the past few years. And today I will talk about this energy-dissipative evolutionary Kolmogorov-Arnold networks for complex PD systems. And this is a joint work with my postmaster, Professor Guan Ling, as well as my colleague Jiahao Zhang at Purdue University. And in briefly, so this is a long title. So in brief, what our framework is, short abbreviated for EVO-KAN. So now let's briefly walk you through the outline of today's talk. So first, we will begin with a motivating introduction on the time-dependent PDE modeling and challenges in data-driven predictions. Then I will introduce the key components of our framework. We start from the Kolmogorov-Arnold networks, or abbreviated for KAN, and then we will talk about the evolutionary deep neural networks, and of course the scalar auxiliary variable, or SAV, approach for enforcing energy stability. And after introducing this framework, I will share a series of numerical experiments, including 1D and 2D Allen-KAN equations and the 2D incompressible Navier-Stokes equations, and then we will wrap up the conclusions and directions for future work. So let's first talk about let's first look at the introduction. So in fact, I work many applications in the fluid problems. So in fact, at the heart of many fluid mechanical problems lies the task of predicting the time evolution of flow states. For example, this is turbulent channel flows. And so the essential question is, given initial flow state, how to predict the time evolution in the future. And in the PDEs, so this is described by this Navier-Stokes equations. And as we all know, that Navier-Stokes is very complicated or complex or chaotic system, not only because it involves the transport phenomena or diffusion phenomena, it involves also the nonlinearity, which would cause the chaos or turbulent behavior. So, so this motivates our task. So given this initial condition, how do we efficiently and accurately predict the system's evolution over long time horizons? So now let's look at some time evolution using neural networks. So most flow evolutions can be formulated as following partial differential equations as partial u over partial t minus n of u, where n of u represents a nonlinear transport or diffusion of more complex operators. So recently, actually there have been many developments in applying neural networks to solve such systems. So there are many, like I think there is two groups of different way. One is the physics-informed neural networks. So including Professor Keniadakis, Patty Karras, and Racing, and so on. And another group of methods, they use the operator learning, just like DeepNet and Fourier neural operator. So and also there are some other some other methods. However, there is what they do is they use a typical neural network is they have inputs that has the spatial variable x1, x2 up to xn, as well as maybe some t, and they have the output that for the u1 to uk, and they have the parameter that w represents the weights inside the neural networks. So there is a this method all relies on the universal approximation under mild conditions, and they rely on the efficient gradient evaluation by automatic differentiations. So they such as partial u, partial x, and partial u, partial w. However, there is some challenges of this neural networks approximating the time evolution of the complex systems. So, for example, PIN usually represents the whole spatial temporal solution as one single network function. So this means this means they may not incorporate the original PDE's time correlation relation. And also, like PIN or DeepNet often need retraining of the network for further prediction. So for example, if we need much longer time than the training period, then we may need to have more data to retrain the neural networks. And besides these two, like a framework, also like when we use the neural network, the standard, we usually use the standard multi-layer perceptrons, which is short for MLPs. MLPs, they use like a ReLU function or other functions. They are prone to overfitting or have a vanishing or exploding gradients. And this way, it means it lacks the scalability, or sometimes it may have some issues when we have this auto differentiations. So now we come up to like our key insights for like to handle this challenges. We consider the following two components. One is called the evolutionary deep neural networks. So this means we only represent a spatial solution using the neural network, and then match this neural networks using the governing equations. So this means we update the neural network using the original PDE. for the system. And then and another replace for the MLPs is we using the Kolmogorov-Arnold networks, or KANs. And KAN uses actually the learnable B-splines as activation functions. Then this is more interpretable and it is more flexible. Now let's look at look at more details about about our evolutionary Kolmogorov-Arnold networks. So let's first look at Kolmogorov-Arnold networks. So we first revisit a classical result called the Kolmogorov-Arnold theorem in the functional approximation theorem. Actually, this theorem states that any multivariate continuous functions can be decomposed into sums and compositions of univariate continuous functions. In other words, for any smooth function f, which depends on x1 to xn, we can always write the following decomposition as in equation 1. Well, this phi qp is a function from 0, 1 to r, and phi q is a function from r to r are just continuous univariate functions. And this remarkable result reduces approximation of high-dimensional functions to learning univariate functions. And also motivated by this theorem, I think in the last year, the Ziming Bill and others proposed this KAN, or the Kolmogorov-Arnold networks. And in particular, this so a KAN is specified by a layer-wide sequences N0, N1, and NL. So well, Ni is the number of neurons in layer I, and XLI is the activation function of neuron Li. And each connection between the neurons associated with learnable univariate spline functions. So instead of scalar weights, we have the function value parameters along edges. More precisely, each layer computes the following as in equation 1, where this VLJI is a univariate spline with trainable coefficients. And this edge-based structure gives KAN a key advantage. The first is it has a local adaptivity across different regions of input space. And the second, it has a better interpretability compared to conventional MLPs. And in deeper networks, we compose multiple such layers to build more expressible representations. And this is actually the matrix form of this deeper KAN framework. And in particular, a full KAN is composed of L such layers applied sequentially to the input vector x0. Now let's look at more about how we combine the idea of the evolutionary deep neural networks. And before look at the combination, let's first introduce what is this evolutionary deep neural network, or abbreviate for EDN. So usually we consider the general nonlinear PDEs of the following form. Well, we have this partial u of partial t plus n of x of u, where n x of u is a nonlinear differential operator, and also such system has the initial condition is described by ux0 equals to fx. And what actually the EDN do is we model we approximate PD solution U using a neural network with L+1 layers, and then Here, the GL+1 denotes neurons at L+1's layer, and the WT represents all time-independent network parameters. Then a full connected multi-layer perceptron is defined as the following as in equation 8, where the GL as neurons in layer L and the WL/BL as weight matrix and bias vector. And the activation function is denoted by sigma. And the input to the network is the spatial gradient is G0 equals to X. X can be equal to X1, X2, or to XD. And then the time evolution of the neural network solution can be represented by the equation 10, where the partial U over partial T equals to partial U over partial W, which is the weights of neural networks, times the partial W over partial T. And the dynamics of the systems then are encoded into this W term, and it can be evolved over time. And we can derive the evolution rule by minimizing or calculating the following optimization problem. And this is actually the least square optimization at each time step. And we can use this formula to determine the update direction for the parameters. And the first order optimality condition is given by the following equations. And with this in mind, we can always approximate the solution by solving the equation 13, where the J is the Jacobian of the network and N is the PD residual. And here we actually use auto differentiation to compute the Jacobian J and this nonlinear term in the PD residual. And with this in mind, actually, we can always use this formulation to update the neural network representation of PD over time. So we will come to more details later. So, but before that, we will introduce another important component to our framework. So in fact, this is called the scalar auxiliary variable approach, which is short for SAV approach. So we use this approach is we want to ensure the energy stability in the simulation, and especially for the gradient flows like the Allen-Kane equations. The SAV method introduces actually a scalar variable R, and this R is associated with energy function, functional, and E, and reformulate, and then we can use this way to reformulate the system so that we can just need to solve the. We can reformulate the gradient flow as follows, and this just leads to a linear system with constant coefficient at each time step, which are computationally efficient and unconditionally stable. And in the context of the framework, we integrate this SAV mechanism to stabilize the evolution of network parameters and enforce the physical consistency. And now let's look at the overview of this EVO-KAN framework, and we put everything together. So here, just to wrap up, is the EVO-KAN framework combines the following component. The first is the spline-based architecture of Kolmogorov-Arnold networks, and the second is a dynamic marching strategy of evolutionary neural networks. And the third one is the SAV method for energy stability. And this means what it means is let's start from given the initial condition. So suppose we are given an initial condition of the PD system. We first represent this initial condition use the KAN framework, and now and here we have the parameter inside this KAN called K, and then we compute the PD residuals and it's Jacobian with respect to this K, and this is all done by auto differentiation. And then what we do next is we solve a linear square system at the following time step for this gamma. And once we got gamma, we have a time step size. We can update our KAN parameter like a K to the next time step. And once we got this KAN parameter at t equals to the next time step, we can always do the same thing to another time step, and we can repeat it again and again until to the time that we want. And the whole procedure actually results in parameter evolution governed by the same PDE we aim to solve, and it's completely bypassing the need for retraining. So it does not need to retrain the neural network. Okay, so now let's look at some numerical test. So we begin with this one-dimensional KAN equation. So this is actually a prototype model for phase separation with metastable dynamics and sharp interface formulation. And the equation, the one-dimensional KAN, is given by the equation 16 to 18, while the 17 is initial condition, 18 is equation 18 means the periodic boundary conditions. And here we so I want to emphasize, we start with some like a sign initial data, and we can choose different alpha values. We can choose different like the pi values. Here we just choose equal to 1, and different sign modes will lead to different interface configurations. And now let's look at some results. Actually, we compare the different epsilon values inside this KAN equations. And I want to emphasize, with smaller epsilon values, the more challenging the problem is, because it gets more steep when as the time involved. And so for our so we compare the benchmark solution with our evolutionary KAN, EvoKAN framework, as well as the evolutionary deep neural network without KAN, just use MLP. And we found that our solution actually, our framework EvoKAN actually accurately captures a curvature-driven motion of interfaces, and it remains stable and accurate under coarsening, merging, and annihilation of domains, and it's better than the EDN in both accuracy and the quantitative fidelity. So we have not listed. So from the figures, we see that actually for EvoKAN and EDN, they are quite similar. But if we take a deeper look at this graph figures, we found that actually, especially the last case, our results, it's much better than the EDN when we compared with the benchmark. And actually, this also reflected.
Sorry, what is EDNN? Is just again evolution pins, evolution neural network.
Yes, yes. So EDN is just the evolutionary deep neural network with just the MLP.
And for the KAN, you are using splines.
Yeah, yes. So EDN does not use splines, but EvoKAN uses splines.
Okay.
One question. So both have the same strategy. The only difference that EDN you're using an MLP, and in EvoKAN you're using a KAN, right? But
yes, exactly.
Okay,
yes,
so
exactly.
it's okay. Yeah, thank you.
No problem. And we see that actually our framework is better than the EDN. Now let's look at the.
You have tables. You have some, because the this is like the naked eye norm. Do you have tables or for the actual errors, quantitative?
Yes, that's a very good question. We have a table in our draft, in our submitted draft, but this presentation I didn't list these numbers. So, but what I want to say is the EvoCAN is about one order more accurate than the EDN.
Hard to believe with the if you
So
use
especially
if you use Chebyshev, it's fine. I know, I see the results, but
okay.
hard to believe. If you use Chebyshev, I would believe it, but I don't think that with splines you can get these results. We work with this KAN, so that we have published several papers.
So here I want to say that for the EDN we just use plain evolutionary deep neural network without any further tuning. So and here
still it's better than splines. So anyway, just keep going.
Okay, thank you. And also we consider this two-dimensional Allen-KAN equations, and so this models the interface evolution in the 2D spatial domains, and the governing equation is given in equation 20, and we assume we use the following initial conditions as in 21, and here we have some parameters. We have one parameter called alpha, and we actually here we choose different alpha values to test our regimes, and again, for the boundary conditions, we use double periodic boundary conditions as in 22. And this is the results for three different for benchmark and EvoCAN and EDN for the parameter alpha equals to 1. And so for this case, actually, so EvoCAN and EDN, they perform quite similar. So there is a very slight difference between them. But however, if we make the alpha equal to 2, this means we have a more sign or more modes there. And we found this seems to be a different story. And for our method, although we have when we take a very deeper comparison, we found that careful comparison, we found our method is not exactly as the same as the benchmark, but we could say compared with EDN in the same scale, we are much better. And now let's look at the last numerical test case, which is 2D incompressible Navier-Stokes equations, which is much challenging than the which is very challenging case. And here, so we have the equation 23 for the NSE. We have a equation 24 for the incompressible condition, and we have and we choose the equation 25 as our initial conditions. Here again, we use the double periodic boundary conditions for the boundary conditions. And here again, so if you're not familiar with this case, so I would say this V is actually a velocity field. It has two components. One is U, another is V. U means the X direction velocity. V means the Y direction velocity. And P is the pressure. And here nu is the kinematic viscosity here. And here we choose this viscosity terms. And actually it is related to the Reynolds number. And the 23 in particular is usually actually describes the momentum evolution over time, and the second is just the incompressibility. Now let's look at, so this is actually the 2D Navier-Stokes equation benchmark solution with viscosity equal to 0.05. And in fact, with some, it starts with some like just two simple initial conditions, and as the time evolution, and it will become some kind of, it shows some different structures. And we just compare our benchmark with our EvoCAN solutions. So here, so we have not listed the EDNN solution is because it just does not generate the comparable solutions. So here we only compare the benchmark and the EvoCAN. And one thing to note that for the EDN, we just use vanilla or just a plain vanilla plain EDN. We do not do much time tuning it. So with more time, if you tune in those parameters, it may get some better results. But for the EvoCAN, actually, we also don't use much time to tune in these parameters, but it gives us some good results. And we found that at a certain time, and we compare with this benchmark solution and the EvoCAN solutions, we found actually they match as well. And for this case. And now let's look at a smaller viscosity. So for the Navier-Stokes equations, the smaller viscosity, the more challenging it is. And from this regime, we obviously see that starting from the initial conditions, it get more chaotic or get more complicated structures over time. And again, we compared with our benchmark and this EvoCAN at a certain time snapshot, and we found still again. So our EvoCAN solution matches well for this benchmark. Though, if we take a deeper look at this vorticity, there is some mismatch here. But I think this is not surprising as for this viscosity number, though it's not a turbulent setting, but still it's more challenging than the previous case, such that we can get a slightly worse solution as the previous case. Now let's look at some conclusions. So what we do is we propose a novel framework called the evolutionary Kolmogorov-Arnold networks, which is EvoCAN for time-dependent PDEs. And we replace this MLPs with spline-based basis functions, which enables the smooth, flexible, and localized representations. And we leverage and this method actually leverages automatic differentiation to compute spatial derivatives directly. And and for this evolutionary framework, it represents only the instantaneous PDE state and reducing the network complexity and preserving the time causality. And because of this, it is capable of long-time simulation, even in some chaotic regimes. And we show that our results our method work across many different PDEs, including the KAN and the Navier-Stokes equations. And this is some future work direction. In the future, we plan to develop adaptive architectures to refine splines in regions with sharp gradients. And then we want to extend this EvoCAN to more complex geometries and boundary conditions. And we are considering integrate this EvoCAN with reduced models and data simulation and uncertainty quantifications. And we also want to apply the EvoCAN, maybe change add some more components to the turbulent flows, because in the previous Navier-Stokes equations, we are not showing actually the turbulent regime. And this is a reference of talk, so it's actually posted in the archive. If you are interested in this work, you can scan this QR code to get this reference paper. And thank you for all.
Thank you so much. So now we open the floor for questions. Do we have any questions for our speaker? Any comments?
You have error plots, for example, in the paper. Maybe you can open the paper. You have not this type of plots. Error versus time in time. Because that's the contribution here is the evolution through the SAV and the method that you said. So I want to see how the error grows in time. You have that?
So in the paper, actually, we don't have this one. But
that's the main thing in your paper about evolution. It's how the solution changes in time. And therefore, you need to look at the error, how that changes in time.
Yeah, that's a really great point. We haven't like plotted this arrow change over the time, but we can add it yet into our drafting.
Because that's what you want to see. First of all, is if SAV actually helps you, or you can just have a standard method that, because the people have done that before, where they use. I mean, I don't know what version of the ADNN. It was something that you implemented, or somebody you found it in the literature. The ADNN.
So actually for the EDN, my colleague Zhang implemented it, and
he uses the same SAV. He used the same evolution method.
Yes, he used SV. Yes, he used the SVB method.
Same as the EvoKAN. The only difference is that the representation in space.
Oh, so sorry. So for the EDN, so Jiahao does not use the SAB method. This is
okay, so then that's what I'm saying. You're not comparing the right stuff. Because somehow, anyway, I think the big errors come from the time evolution, not so much from space. So SAV may help you a lot. SAV is a method of Jishen, right? The method that Jishen introduced, right? For splitting.
Yes.
Okay.
Yes.
So you have a conditional method. Yeah, that's fine. I've seen that before, and I think Jishen and Ziping Mao have a paper on something similar, except they don't use KANs.
Oh, yeah. Yes. So here's one thing I want to emphasize is that when we compare this EvoKAN ADN, and another thing is important in the spatial. So usually when we train this, we use the same parameter numbers to approximate the initial conditions. The EDN usually may not give you the long time simulation results. So it may just shift off at a certain time. But the EvoKAN can give you like a better evolution over time. So this is what we have also seen.
Right, but it's not because of the KAN. It's because also of the SAV. That's what I object to.
Yeah, I totally agree.
You're not comparing two. You're comparing apples and oranges.
Yeah, that's true. That's true. So here, so just let me just like for different cases, let me just rephrase it. For the Allen-KAN equations, no matter one-dimensional and two-dimensional, we all have this SAV for EvoKAN and EDN. But for the Navier-Stokes equations, for no matter if for the Navier-Stokes equations for the EDN, we do not generate reasonable results when we use it. And what we found for the 1D and the 2D Allen-KAN is with the same amount of parameters, even with both with the SAV, it evolves differently, especially for the EDN. At some time, it will have some slightly shift off over a certain time. So we doubt. So we don't know what happened, but we doubt it is because the EDN EvoKAN uses a spline, so it is more smooth when we do the differentiation. But for the EDN, it uses it is just they do not use spline, so they may have some like small errors when they do this differentiation. And this is also seen from this test case. So if we compared with this initial condition in the bottom to the top, we found actually it has more like a steep structures here. So we doubt when we use neural network to represent this initial condition, KAN have a better ability to represent it, but EDN with MLP may not. So of course, we can like train much more time to get a better approximation, but it's much more expensive to do that.
Okay. Thank you.
Thank you.
Yep. Do we have any other questions from the audience?
Yeah, actually, I would have. Hi, my name is Sasha, postdoc at Brown. Turning on the camera, it should pop up immediately. So it's more of a technical question. Regarding the parameterization of the weights, did I understand on the biases or whatever you call the parameters? Do you understand correctly that you don't explicitly parameterize those weights and biases, but you use the availability of a gradient of those parameters that's given implicitly by the network definition? Did I understand that correctly, or do you define weight is some function with some hyperparameters?
So we are not. So actually, what we do is we represent the initial conditions using the neural networks, and then we can use this basically equation 10 to 12 to solve this optimization problem at each time step when you involve it. So this is what we do. So we do not do a particular assumption for the weights itself. Of course, when we updated it, we use the SAV method to approach to ensure it is energy stable. So this is actually what we do.
Okay, gotcha. Thank you.
No problem.
Do we have any other questions, comments? I don't think so. So thank you so much for your great talk. And I think it's time to close the session. Thank you everybody for joining us today. Have a great weekend ahead. Bye.